Exoplanets. Love this topic because one of the reasons I wasn't keen on teaching Astro 5 for the first number of years I was at UCLA is that this topic didn't exist. There were no exoplanets because I knew that even as difficult as the challenge of finding other planetary systems is, it was maybe one of the most important things we could be doing. And so even if the odds were low, I figured we had to try. And since I was on a telescope allocation committee, I always tried to defend the proposal by the person who eventually did discover them with that telescope, even when a lot of other people wanted to kick him off. That we're tired of this. This is not going to work. This is hopeless. Let's just give up. We've already reviewed the general argument that when a star forms, there should be leftover material with some spin left over, which settles it down into a disk. That's a natural protoplanetary disk location where condensations could lump together if material, small dust grains, molecules and so on, can orbit around in roughly circular orbits and at relatively low velocities stick together and coagulate. It's basically the electric force. They get a little bit charged up, and so you can have larger and larger clumps coagulating with each other. They touch very, very gently and stick. They are rather sticky. And if the temperatures are low and the motions are nice and smooth and circular, eventually the objects get to be big enough that they have an additional gravity, and so there's extra gravitational pull pulling on other material that wants to then come in and join the growing object, and that's a kind of a runaway process. The big objects get bigger, they get a stronger gravity, thus drawing more material on, and those bigger objects are called planetesimals, and there certainly were a lot more than 8 of them, or probably even 8,000 of them when our solar system got going in its early stages, but there's just a relatively few number of surviving winners who are here now, and the others are mostly swept up, having fallen into our planets, or they're in the outer solar system as comets, or they didn't get to be planets, maybe like asteroids. So the question is, would that same process happen when another star forms? Why shouldn't it be similar to the processes that the sun went through when it formed? I haven't said anything that's special or unique about the sun. One week I'll be saying, oh, how special we are. We're just so lucky to be here. And then, on the next week I'll be saying, yeah, I don't think that this is that unusual. There must be other cases around the Milky Way galaxy where the same thing happened. So I'll give you the arguments on that. I'm sort of following that theme in this lecture. But of course, most of what we have to assume about those other stars, we have to use the only information of the only system that we have vastly, vastly more information about our own system. The fact that we have any information about any other planetary systems, exoplanet simply meaning a planet outside of our sun's solar system, is an amazing development. I think I already showed some pictures of some relatively young stars. The star is underneath the black circle. It would blow out the entire photograph here, but you can see protoplanetary disks. I can't help but mention that the discovery was made by UCLA astronomers, but even more beautiful, spectacular images have been obtained of protoplanetary disks now. So the first part of what I said, we know, at least in the early stages of a young star when it's just formed, we do see these protoplanetary disks. Then eventually they dissipate somehow, but they may have left behind some planets. That's the question. These are kind of easier to see than a teensy little planet in there, right? You've got the glare of the star, which is just millions of times brighter, and this little planet is going around here. It's so much fainter than this disk that it would seem, and you might be right, virtually impossible without super special extreme optical instruments to ever isolate and separate the light coming. It's be reflected starlight, I guess, maybe, unless the planet was glowing with its own light, its own heat. But even to see the planet would be beyond our capabilities. Does that mean that we can't know if a planet is going around a star? No. Astronomers, as you know, are sneaky and clever, and so we're not limited to necessarily just studying things that we can actually see the light from. I think you may have heard this story before. That's almost one of our specialities, is uncovering the covered and seeing the unseen. So these disks, at least in the early stages, are not unusual. So then what happens? Once a star starts shining fairly brightly, it tends to blow out the dust grains in the disk, and they as I said, they tend to go away after millions of years, but that still is enough time. It was certainly enough time in our solar system disk, and it's enough time perhaps in other stars, protoplanetary disks, to form the planets. Gentle collisions bring particles together, and eventually the particles make large enough objects that they have a little bit of gravity, and then they start a runaway process of sucking in even more material to build up these planetesimals to hundreds of kilometers size objects. And then, of course, a relatively small number of them survive to be the planets we see today. And as you can imagine, there's fairly big spaces between the planets. That's not too surprising because all the planetesimals that might have been in those spaces in between would have eventually collided with one of the existing planets. All right, so how are we going to find the planets now, particularly if it's too difficult to actually see light coming directly from those planets? The idea that was pursued by the 120-inch telescope at Lick Observatory that I was on the time assignment committee for, the idea that was pursued then seemed like the only possibility. It seemed very difficult, nearly impossible, but the only thing anybody could think of, which is don't look exactly for the planet, look for the effects of the planet's gravity instead. And maybe if you're lucky, you measure very carefully the exact motion of the star around which the planet goes. The home star, the host star, maybe you will see that star wobbling periodically back and forth. And of course, something doesn't accelerate for no reason. It can only be accelerated periodically back and forth if there's some other object, presumably a gravitational object, even though we can't see it, which is going around it and periodically pulling it, accelerating it towards whatever direction that orbiting body, that exoplanet, might happen to be. I have just described to you the Doppler method here. That's the bottom one. Maybe I should have put that one first, for searching for planets. And we'll talk about that more. And that was the original method. When I talked about looking for planets before any of them had been found, I basically dismissed the other sort of more intuitively simple search method that you could use because I thought that this second one here was utterly ridiculously hopeless. And I guess, most of the sophisticated astronomers in the know also thought this was hopeless. I love it when we're wrong. We're wrong. This actually worked spectacularly well, but it's even more difficult. So but it's an intuitively simple idea. I don't want to, again, look for the planet itself or its light. I'm going to look for the absence of it, the opposite of that, if I'm lucky. If I'm lucky enough that the planet will happen to pass in front of the star that it's orbiting around, which I guess in principle would happen once per orbit. But you realize there's quite a matter of luck involved here. The orbit of this system, it has nothing to do with us. It doesn't know which way the Earth is. But by lucky accident, the orbit of this system has to be in a plane that happens to be perfectly lined up with whatever direction Earth is, whatever the direction the astronomers are observing it. If we're observing it from even ever so slightly the wrong angle, we would never know that there was a planet there because it's not going to make an eclipse of its home star. That's a transit technique. This would take an incredible amount of luck because I don't know, less than 1 in 100 planetary systems is going to be seen exactly edge on so that you'll be able to see those eclipses of the planet moving forth. It's just luck. Most of them is going to be a wash and you'll never know about it. And second of all, even if you were looking at one that's exactly edge on during the eclipse, the planet is so small compared to the star is so big. I mean, even let's think about Jupiter. What is that thing? I don't know. It's about 100th of the diameter of the sun. We can look up what the numbers are. And it's not just the diameter, it's the amount of area that Jupiter would block out of the sun. So that would be just 100th squared because area is two-dimensional. So at the best, if you're looking, it helps to have a big planet to cast a big shadow. But the best you could think of with the transit, you're talking about looking for occasional. You can't predict when it even happens. You just keep staring and staring, and you're looking for like a 1 in 10,000th decrease in the star's light for a few hours, and then it's back to normal again. Think about the observational challenge, the total impracticability of doing such a search. Anyway, so that's why we all thought that it was impossible to do that. So let me concentrate on the thing that we thought maybe was possible and turned out that it was possible and gave us the first discoveries. It just comes down to Newton's laws of gravity. What does Newton's third law say? If let's take a Jupiter, for example, big planet, a lot of gravity, a lot of mass. Obviously, Jupiter is going around the sun in almost a perfect circle because the sun's force of gravity, it's a mutual gravitation, is pulling Jupiter towards the center of the sun. So that's the force of the sun on Jupiter. But what does Newton's third law say? Newton's third law is the law that guarantees that the total momentum of a system is constant. So if one object pulls on another object, this can only work if the second object is pulling back in the other direction on the first object with it's called we now call them forces. Newton called them actions and reactions. But anyway, it's a force in the opposite direction, and it only works, what does Newton's third law say? If the force pulling back, in other words, the force of Jupiter's gravity on the sun, has to be in the opposite direction, exactly equal to the force that the sun exerts on Jupiter. It's just in the opposite direction. There's your third law. So if there's a force acting on Jupiter, then there's also a Jupiter gravity force causing the sun to accelerate back and forth. And how much does it accelerate? Well, Newton's second law tells us that. I always write Newton's second law as A equals F over M. Isn't that a much better way to F equals ma? It is not very useful, but A equals F over M is very useful. So that's why this is such a subtle effect. The force is the same. The force of Jupiter on the sun is the same as the sun on Jupiter. But the masses involved are so different, right? The sun is thousands and thousands of times the mass of Jupiter. So it has so much more inertia that the sun is only going to be accelerated around by 1,000th as much or less, I don't know exact number, as Jupiter is. So really, it's such a small effect. It's going to require excruciatingly precise measurements, more than astronomers were ever used to doing. So the acceleration, but at least the star has light. Doesn't have to be the sun, right? So at least if we could measure the acceleration of the star going back and forth, how would I do that? Doppler effect, periodic variations in the velocity coming towards us, going away from us, coming towards us. If I could measure that, then I could infer that there's a planet present, but the acceleration is going to be only in the proportion of how massive the planet is compared to the mass of the star. So this clever idea, it's a nice idea in principle, only has a chance, honestly, of really working if you have a pretty massive planet that, I don't know, maybe is at least 1/10,000th or 1,000th as massive as the star. Otherwise, we'll never be able to see the effects of its gravity. It'll just be too small to measure. Even Jupiter doesn't have much of an effect on the sun's motions at all. And the Earth, yes, it is closer. That helps, but it is so small. I mean, this would seem to be impossible. If you just had the Earth and you had no If you had only a system with the sun and the earth around it and nothing else, the sun would move back and forth once a year in a periodic orbit. Actually, the technically correct way to say this is that both objects would be orbiting around the center of mass of the system. But where is the center of mass of the system of the solar system? The center of mass of our solar system, well, of course, it's not at the center of the sun, but it's inside the sun. I mean, the mass is, it's like a seesaw. There's so much weight on the sun that is very close to the center of mass. The center of mass is underneath the surface of the sun, and it's not in the center. It's offset somewhat in pretty much whichever direction Jupiter happens to be at that time. That would be where the center of mass is, and a little bit offset also for whichever direction Saturn might happen to be, and that's about it. So the real true statement, if you want to be Newtonianly correct about this, is that all of the planets, in fact, even the sun, everything in our solar system is all orbiting about the one common center of mass. The sun's orbit is very small. It's just a wobble. I mean, it doesn't even wobble by its whole diameter back and forth. And the planets go on pretty large orbits, tens of millions, hundreds of millions of miles across, all going around that same center of mass. If you only had the Earth's gravity, which isn't that much, the acceleration would be very, very negligible. The sun is moved around, like I said, it's pulled back and forth every 365 days by the Earth's gravity increasing and then decreasing its velocity that you could measure if you had incredible precision measurements of about changes of velocity of 1 meter per second. I mean, I can walk that fast. So the sun will be going this way for 6 months, and it'll be going this way for 6 months. How is anybody going to measure 1 meter per second when the speed of light, that's our reference standard that we're going to be measuring wavelengths with respect to, is, 3 times 10 to the 8, 300 million meters per second. You would have to be able to measure shifts in wavelength of smaller than 1 part in 300 million. Is that even possible? Right at the edge. Only very recently people have started to try to do this. It's excruciatingly difficult because even the motions of gas on the surface of the sun are faster than 1 meter per second. It's bubbling up and down. Anyway, so this is just a diagram. All right, so there's the sun. This is actually exaggerated to make it look easier than it really is. There's the sun over here. There's Jupiter over here. Actually, the center of mass of the solar system is really inside the sun. And it's true, though, the sun wobbles around once every 12 years as Jupiter goes around on the other side once over 12 years. They're both going around the center of mass. Actually, it's a little more complicated than this because you all have to include Saturn and so on. So if you were in outer space at a distance, I don't know, about 30 light years away, you would see these absurdly, unmeasurably small actual motions of the sun moving around. This has not been possible to measure, but we might be able to measure the velocities. So don't even think about this astrometric method, looking for the star actually move around. Don't have the precision to do that, I don't think, for decades. But we could look for the very small Doppler shifts changing. Amazing discovery. Remember it well, that some objects in binary systems were so small that they weren't stars. What I mean by stars, remember the definition there? They weren't massive enough to get hot enough in their cores to where they could steadily burn hydrogen through fusion reactions into helium. So they couldn't really make it as stars, but they were bigger than planets. They were basically, I'm going to say, something like a few percent the mass of the sun. They're basically failed stars, and I'm not really interested in them in this course. There are lots of them. Because of course my general principle of nature is there's always more small things and insignificant things and less massive things compared to the big ones. The big ones are always the rare ones. That's true of galaxies, it's true of stars, planets, everything. What we're looking for is going to be even more difficult to find because we're looking for objects that are even smaller than a brown dwarf object. We're looking for things that might be no more than 10 times the mass of Jupiter. Very big planet that's very close to its star. Nobody expected to find was discovered by European astronomers first. So they sort of scooped it. Like with a few months later, the California astronomers had discovered like 20 planets. Anyway, but they didn't publish first, so they didn't. Yeah, they didn't get the Nobel Prize here. So this is the original discovery data. This one is much bigger than 1 meter per second. This is the motions of the star. The star is called 51 Pegasus. It's in the constellation of Pegasus. And this star moves back and forth really rapidly. Like the whole thing goes through one cycle in like 6 days here, 5 days. And it's moving back and forth by 50 kilometers a second, 57 meters, no, not kilometers, meters per second. Two complete surprises here, or they lucked out. First of all, they found a planet, surprisingly, that was very close to the star. A year on this planet is only 6 days. Sorry, 4 days. Okay, it's less than a week. Who would have expected that? Even Mercury it takes a few months to go around the sun. So they just lucked out in finding a planet that's so close to its star that it has an enormous gravitational acceleration, much bigger than what we were expecting to be looking for. So much easier to detect this. Plus, it's a really massive planet. I don't know exactly. I think this thing is something like 10 times the mass of Jupiter. Whoa, this is really messing with my mind here. What kind of planetary system are you talking about? The massive gas giant planets in our solar system are way out there, and I told you why. All those gas giant Jovian planets needed to form where temperatures were very low, long distance out. In fact, that is probably where they do form. That way they can hold on to all their light elements, all their hydrogen, helium, and they can grow up to have enormous masses, and they don't lose anything because of the heat being nearby to their star. Well, presumably that's what happened in the 51 Pegasus system too. Some very big planet, even got to be much bigger than Jupiter, must have formed fairly far out, a long distance away from the star. But then somehow this planetary system evolved rather dramatically so that this giant super Jupiter gradually shrunk its orbit and spiraled in closer and closer and closer until it ended up, must have wreaked havoc, messed up everything else that was in that planetary system until it settled down in a super close orbit right around 51 Pegasus. Weird thing that nobody was thinking about, no one was predicting it, no one was looking for it, but it was so easy to discover. Massive planet right next to the star, so it's hot, it's heated by the star, unlike Jupiter. It's called hot Jupiters. So if there were any hot Jupiters out there, obviously this method was pre-selected to be able to find those. This method is still really not capable of finding Earth-like planets. They're too far away and too low a mass. Once you found one, though, you could go and look for additional velocity disturbances that weren't explained by the first planet. So this is an example of another one. You can see that, yes, I don't know how fast this is. These are 1,000 days here. So every few weeks, the star, this is the star's velocity. This is even a bigger one. It's really accelerating back and forth because of this, this hot Jupiter is moving it back and forth hundreds of meters per second. But then superposed on that motion, there's also a gradual motion as the star gets pulled around, what is this, over the course of a few years. And that is caused by an outer planet that's on a much larger orbit. And remember, the gravitational acceleration from both of the planets is influencing the star. And so you can actually work out that there's more than one planet present in the system. And of course, if you could look for even different periodic motions or accelerations of the star, you could perhaps pick up a third or a fourth planet. I mean, once you know there's one or two there that you were able to see, you have to be very suspicious. There probably are a number of others that you just haven't been able to see yet. Why the hot Jupiters, which nobody expected, were the first things to be found and are still among the most widely known planets. But I don't think They're the typical planets. They're the ones that we know about. Okay, this is such an important theme in science that you get a lot more data about the things that are easy to find, and you're in the relative dark, literally, about other things that may be more common and more numerous, but they're more difficult for you to detect and measure. The exact analogy, and I mean, I've seen this in person. A scientist, an astronomer who's trying to go out and look for planets reminds me very much of a person who found himself leaving a fraternity party. I guess it could be a sorority party, but it really works better if it's a frat party. And this person has very impaired senses for some reason. Person is having a difficult time because he's dropped or lost his car keys. Now, if you think about this story, it's really wrong on a number of levels. First of all, this person should have had a friend who should have said, "You're in no condition." After that argument failed, then a passerby notices partier is just searching around, well, sort of crawling around on the ground in a fairly small circle by a lamppost. Are we looking here because you think that you dropped your keys somewhere around here? Is this where you're most likely to find them? And then the inebriated partygoer says, "Man, I have no idea at all. If I drop them anywhere else, I'll never be able to see them at all." Astronomy is so much like that, except for the alcohol part. In fact, a lot of sciences, you just search where you can find stuff. Not necessarily does that mean that the keys are there. Doesn't necessarily mean you're finding everything that's there. This was a fun one. After removing the motions of these two planets, even a third periodic oscillation down at only 10 meters per second caused by a third planet and its gravitational acceleration was able to be found in this system. Really spiffy. That's why the Doppler technique was a success, because we were lucky, because it turns out that a number of stars do have these hot Jupiters around, and this technique is really good at finding them. So we know about quite a lot of these hot Jupiter planetary systems. I'm not that interested in hot Jupiter planetary systems because we have already been extremely dismissive of Jupiter. If you remember last week, I really was not impressed at all about gas giant planets because I didn't think that they could conceivably be habitable, at least in terms of life as we know it, worlds. Although they could perhaps have some moons around them. That might be another story. So maybe they're interesting anyway. But what you're really interested, of course, in is like Earth 2, aren't you? You're really interested in a habitable rocky world. Unfortunately, those planets would be much smaller than Jupiter. And in these hot Jupiter systems, they may not even exist at all because they may have been hurled out of their orbits, if they did exist, by this big bruising planet moving in to take up a position so close to its star, probably made it extremely difficult for any other stable little Earth planets to survive in such a system. What about this other technique that I thought was impossible and turned out to be wrong? I'm not afraid to tell you when I have made a mistake. Here's an illustration of it. There's the sun at sunset, and that may be the image of Venus. You've probably seen a picture of those rare occasions when Venus's orbit happens to take it right across the disk of the sun. In fact, we had an observing session at UCLA to see the last transit of Venus. It's rather fun. It's really small. So the total amount of sunlight that's coming from you, even as Venus goes across the disk, it's only dropped out. Okay, get the fisherman out of the way. Guys, okay, move. Get the bird out of there. The total amount of light from the transit, the change of the brightness is of the star or the sun is less than 1 part in 10,000. However, astronomers, I have to say, some of them are extremely persistent. And so they realize that although measuring the brightness that precisely to see a brightness change of 1 part in 10,000 or maybe 1 part in 100,000 is really impossible to do from the ground because you're looking through the Earth's atmosphere. Things are always flickering. The air that's between us and space is turbulent and moving around, refracting, and so on. However, you could remove yourself from most of those difficulties, those artificial sources of flickering and variability, if you would put your telescope in space. And if you were an incredibly compulsive fanatic, you would make a satellite, such as NASA did, called the Kepler satellite. And it started looking very carefully, just staring at basically random stars. There's what Kepler looks like there. They packed it with the largest collection of very sensitive and very uniformly stable electronic detectors. These are used actually in popular cameras now. They're called charge coupled devices. So they could simultaneously watch 100,000 stars because they had no idea which star might be the one that might have its planetary disk lined up to point towards the Earth in the perfect orientation, and might at that moment just have one of its planets transiting across the star to block out the light. Here are some of the spectacular results. Okay, this is a very large transit. It actually knocked out 2% of the brightness of the light. 99% of the systems aren't even lined up, or they're not oriented the right way for us to see the eclipses. But in the 1%, they are lined up close enough, and Kepler has found literally a few thousand eclipsing planets discovered by the transit method. So the transit method now, which I thought wouldn't work, is the most successful way that we have. And it tells you some nice things also. First of all, if you can see a second transit, then you know the period. Right, and remember, you don't even see the planet. You don't really know where it is, except that it's periodically passing in front of its star. But if you can watch a few eclipses, Jupiter takes 12 years to give you one orbit around. But anyway, if you're looking for something that maybe orbits around in a month or so, you might be able to see multiple eclipses, so you know how far away from the planet it's orbiting, because you know the size of its orbit. Second of all, you watch how long the eclipse goes, and then you know and you also know how much of the star's light has been blocked out. If a lot of the star's light was blocked out, that means you're talking about a large planet. Big diameter, blocks out a lot of light. If the eclipse is a very shallow eclipse, that must be because your planet is a very small, dark object. It's a small object, so it casts a very small shadow. These are schematic drawings of the first 4,000 planets. They're marked by the black dots there, these to get the relative size as best they can, compared to their stars. Many planets, even smaller planets, quite a bit smaller than Jupiter, even planets as small as Earth, beyond our wildest dreams. Final method, just to show you that we're not just sitting on our hands with the ground-based astronomy here. We're also trying to do stuff on the ground, including at UCLA. And if you use special high magnification techniques, these are interesting techniques, firing a laser into the atmosphere so you can correct for the turbulence that the atmosphere produces to get higher magnification. Like other technologies that astronomers are now dependent on, this was developed for military purposes. Thank you, Air Force, and then declassified about 15, 20 years later. So using those declassified techniques, you can look at a bright nearby star here. You don't need to know the name of it. And there are, in fact, several points of light around it, which are stars. And you can go back and observe the next month and next month. And yes, these points of light, these planets are indeed orbiting around the star. You can watch them go around. The reason that direct detection, although it is very difficult to do, is very interesting is I'll give you two reasons. First of all, it allows you to see fairly big planets, even if they're quite far away from the star. They might have long orbits, low velocities, and they might never eclipse it. So you wouldn't even know about them otherwise. If you could measure the light coming specifically from this planet, not the light from the star. That's a confusing glare that I don't want. I want to remove that. But if you could just focus and concentrate on the light coming from the star, you could analyze the light carefully to try to determine its composition with spectroscopy. You could at least try to determine what the composition of its atmosphere is if it has an atmosphere. This is largely reflected starlight, so we know what reflected starlight looks like. Just take a spectrum of this, but on top, superposed on that reflected starlight, like if you look at the light from the Earth from a long distance away, it looks kind of like sunlight reflected. But there's also very distinctive absorption due to molecules in the Earth's atmosphere. Actually, there's a fourth planet that was found going around. This is some UCLA people. I guess that's why I put this in here. This goes up to date as of about a week ago. Every dot on here is at least one, it's considered confirmed. Pretty high confidence detection of an actual planet going around its actual star. Bluer it is, the smaller the planet is, the closer to Earth size it is. So I'm particularly interested in these Earth-like planets. The pink ones here are like the size of Jupiter or bigger, which again, I'm sorry to be so prejudiced, but I'm less interested in those. Although it seems like if you're going to have, it seems like they kind of come together, right? One thing I'll say is if you find me some planets that have Jupiter objects around them in fairly big orbits, you probably have found a system that has small rocky Earth-like planets around it too, even though we can't see them because they go together. If one forms, the other probably forms closer in. So you didn't waste my time, is what I'm saying. But what I'm really looking for is these Earth-sized planets, or some of these here would be called super Earths anyway, something that's 5 times the size of the Earth. Up here, we're getting up to the size of Neptune. Doesn't sound so Earth-like. But let's look at the other axis here. So this is the mass of the planet as measured, trying to look at its gravitational effects on its star. So this is the mass of Jupiter. And as advertised, as you can see, most of the planets that are known are like the mass and the size of Jupiter or bigger. Not because that's what most planets are, because those were the easy ones to find. The harder ones to find, there may be lots of these missing, are down here at 1% the mass of Jupiter. Earth would be really like down here. And then what's the second interesting thing I plotted on this diagram? How far away they are from their central star. There's another extremely strong bias. All of these techniques, except for that last one I showed you, it really helps to have, if you want to see the effects of the planet, helps to be very close to its star. But that actually means it's also rather hot because it's heated by the star and might not be very suitable for a habitable planet with life. But here is 1 astronomical unit. Does everybody remember what 1 astronomical unit distance of the orbit is away from the star? That's how far we define it that way. We're Earth, we get to define this stuff. That's 93 million miles, the average distance from us to the sun. And you'll see that most of these planets are actually closer to their star than the Earth is to the sun. Less than 1 astronomical unit. A lot of them are closer than Mercury is to the sun, so they're very hot here. Well, they're certainly too hot to have any kind of liquid water, so they kind of fail Matt's handy dandy habitability test. So I'm sorry, it's very difficult, but we certainly have found a great number of suggestions that even if these habitable type planets have hardly been found in just a handful of cases, they must in fact nonetheless be very common. It must be all over the place. And the reason I say that is if you look at the statistics, like just take the Kepler results of these transits, these eclipses. Remember, we already said you're going to miss 99 out of 100 because they're not tilted the right way. But if you count for that, somewhere between a fifth and maybe half of all stars do show these eclipses. So when you look at them from the right angle, the right viewing perspective. So it may be that, I don't know, a third of all stars do have some kind of detectable planets around them when you look carefully. They're all over the place since there's so many stars, 100 million and 100 billion in the Milky Way. There's even more planets out there. So that's very, very encouraging, even if we're still having a hard time identifying the best place to find Earth too. So I said hot Jupiters almost certainly couldn't have formed there. They must have formed in the outer long distance away from their stars, and somehow they migrated in some kind of friction on their orbit, probably through gravitational interactions with other stuff in the system, which fortunately did not happen too much in our solar system for some reasons there. I like to have Jupiter. It's great. It's kind of, as I said, it's protecting us from comets and other things bombarding us, but I sure don't want it in the inner solar system. I like to have it out there. You stay right there, Jupiter. That's good. Right there. Don't get too close, Jupiter. I'd like you right where you are. Okay, other systems have not had such a happy time. Again, this is basically the same plot that I just showed you. We've got the mass of the detected planet in units of Jupiter. Remember, a lot of them were around 1 times the mass of Jupiter. This is a factor of 10 logarithmic scale because we're dealing with a very wide range of planetary masses. Some of them are 10 times Jupiter, 20 times Jupiter. Some of them are even just 1,000th of Jupiter's mass. And then on the X horizontal axis, I've got how long it takes to orbit the star in Earth years, 365 days. So obviously, Earth orbits around the sun. Earth in 1 year. Mars takes about 2 years to go around the sun. There's Venus, which has about the same mass as the Earth. Look at that. We're not very massive right here. We're just, what is that? Like a few tenths of a percent of the mass, 1/300th, the mass of Jupiter. There's Jupiter at 1 times the mass of Jupiter. Saturn's down there. So you see this rather clear distinction, at least in our solar system. The inner planets are all rocky, similar composition pretty much to the Earth, Venus and Mars. And then the outer planets, because they were able to hold on out there at the low temperatures to their light gases, are 10, 50, 100 times more massive and further out. So I guess everybody was expecting to find some similar planetary systems around stars, except what they really could find more easily with available instrumentation and techniques were planets here which don't have a corresponding analog in our solar system. So let's see what was found. Wow, what was found was lots of hot Jupiters, Jupiters that are very close to the central star because they were so easy to find. Well, how about super Earths? That sounds pretty good, although these are really not habitable either because they're so close to the star that they're going around. I think I put this on the cover of the welcome page to the course website for Astro 5 because I thought this is like one of the most amazing observational findings of the last 5 or 10 years. There are actually 6 different eclipses of different sized planets all going in orbit around this one star, Kepler 11. It's really amazing. Some of these planets are pretty small, right? It hardly blocks out any of the light at all there, right? Why are those dots are the actual brightness measurements taken? And you're going, well, that data doesn't look very accurate. Look, it's like bouncing up and down here. Can't these people measure a brightness accurately? And the answer is no, these people cannot measure a brightness accurately, not to 1 fraction of 1/10 of 1%. This is just the limit of how precise, the instrument can measure light. But it was able just barely enough. If you believe that dip there, I believe that dip, then that corresponds to something twice the size of Earth. Then these bigger dips here, these are pretty impressive, 3, 4, 5 times the size of the Earth, and they all have different periods. You can see this little yellow one is going around on a pretty close orbit. It looks like there's an eclipse every 10 days. Then this outer planet here is going around every 30 days. Anyway, you have a whole family of planets in this system known. As I said, this required a good bit of luck. So I can almost guarantee you that most of those other systems where we only know about 1 or 2 planets, I'll bet you there's another half dozen as well. Just hasn't been found yet. As of 5 years ago, let's see, there were 2,000 known confirmed planetary systems where we just knew about 1 planet going around the star because that's the easiest thing to find. But there were almost 400 systems where we had discovered 2 planets there. You could actually see the 2 different planets going around on different size orbits with different periods. Then there were more than 100 triples. We had 3 planets, almost 50 quadruples. It's getting more interesting. 19 cases with 5 planets detected around that star. And then the most spectacular ones. We have a few systems like I showed you with 6 known planets going around. And then this one, the record holder, because it has 7 planets detected going around it at different distances and therefore different temperatures. Remember from our discussion earlier, the average temperature of that planet is going to be determined almost entirely by its distance from the sun, its star, depending on how bright that star is. Also, to some extent, depending on how much of the starlight gets reflected, maybe by clouds, the albedo or reflectivity of the surface of that object. But basically, we have a pretty good idea of which of the planets might be at the right distance from their stars, given their star's amount of power that it's putting out, to be in the range where their surface temperature could be somewhere between 0 and 100 centigrade, somewhere between the freezing point and the boiling point of water, somewhere in what I call the liquid water or habitable zone. Solar system, we've got, of course, 8 planets here. Kepler 90 also apparently has 8 planets around it. Pretty amazing. And I mean, this is just the first sampling of these. All right, Kepler 62 is a fun one. Here is a scale drawing. That's what I like about this. There's the sun, solar system. Mercury, very close to the sun, hot as blazes on the sun side, cold as deep space on the dark side. Venus, twice as far out, even hotter because of the runaway greenhouse effect, hotter everywhere, the hottest place in the solar system outside of the sun. Earth, right there at just the right distance now to have ice, water, and steam, water vapor, all 3 phases of water found simultaneously on the Earth. And then finally, you get out to the end of this green zone here, Mars. The green zone is a sort of an artist's conception of a rough guess of a possibility of what you might call the sun's habitable zone. Anything that's inside the green zone here is certainly too hot. All the water would be evaporated. Venus, under other circumstances, could have held on to its water, although it failed. But so Venus might possibly, you could argue, it's not certain, could be on the inner edge of what could be the habitable zone if we could find a better planet than Venus. Maybe. Earth is obviously in the habitable zone because I'm talking here. And Mars certainly was in the habitable zone and arguably still is. And if we had some kind of unbelievable terraforming project that, I don't know, resources beyond what humans can imagine in the next million years, maybe we could make something habitable of it. Of course, we'd never get the permits to do that. Now, let's compare that, seriously, to Kepler 62, a less massive and therefore dimmer star, a very long-lived star, not as bright as the sun. So if you want to have a habitable zone with liquid water, this is to scale here, you have to be orbiting closer to this little dim star, or else there's not enough heat to keep liquid water. So there actually are 3 planets within the habitable zone. Sorry, they're too hot. Basically, everything is scorched. The surfaces are molten, and 62b, it's on fire practically. It's so close to the star, so not habitable. But I want to call your attention to the 2 outer planets here, E and F, the 5th and 6th planets, which both appear to be, as far as we can tell, for that star in its habitable zone. What about the pretty drawings here that you often see? These are artists' imagination, beautiful, fairly scientifically based or scientifically inspired drawings are from Robert Hurt, who was absolutely the most artistic graduate student we ever had at UCLA. This is the richest planetary system known here. This is the closest one, so he's making it look kind of like Io. It's like a molten surface here. There's a few, looks like they're in the habitable zone. Maybe they're Earth-like planets. We just don't know enough to say one way or the other, but it's possible. And then there's some that are out there too far, frozen ice balls. Take 1.5, 2.4, up to 12 days. Very close to the star that they're going around. But the star's quite dim. So that's how like a year on this planet is only 12 days. But it still manages to be pretty cold because it's going around such a dim star. if you have enough information, like you can see a transit eclipse, and you can then measure Doppler shifts, and you can measure gravity, and you can measure mass, you could work out some other interesting things about the star. I would like to know the distance that it is from its star. That's fairly easy to do because that's going to tell me the approximate temperature that the planet should be. Then what I'd really like to know is what the mass of the planet is, and then I want to know how big it is, because if I know m and I know r, and these planets are big enough so that gravity has pulled them into spheres, then I know the mass and the volume. The volume is 4 pi over 3 r cubed. So I know the mass divided by the volume, which is the average density. That's the average density is like the most informative thing you could know about the structure of a planet, right? That completely separates the inner so-called terrestrial planets from the outer gas giant Jovian planets. We have the high densities, they have the low densities. We're made of rock and maybe iron. They're made of mostly gas. Here's an approximate diagram from a few years ago where we have some of the most Earth-like planets that were discovered up to that time. And they're shown, they have uncertainties, error bars. We don't know exact masses. They're shown in yellow and orange symbols here. There's a few more on the system now. Some of them are not much more massive than the Earth. Here's the mass of the Earth. There, oh, we put in red, we put our terrestrial planets. There's Earth, there's Venus at almost the same mass, and then there's Mars and Mercury. These are all, remember what? This is the density, about 5 times the density of water. This is like 3 or 4 times the density of water. This is 5 times the density of water. So this brown band here is rocky planets. Why? Because for the amount of volume they have, the mass tells you that they're pretty dense. 3, 4, 5 times the mass, times the density of water. There are actually a few Kepler planets, like around star Kepler 138, which seem to have terrestrial type, rocky type dense planets. Even out here, some of these Kepler planets might actually be rocky, Earth-like, or terrestrial planets. These here don't have a high enough density. They're too big, too fluffy. So they're probably gas giants. Once again, I'm not so interested, unless they have some moons. I don't know when we're going to be good enough to actually look for moons around gas giant planets around other stars. Right now, I'm just going to concentrate on the exoplanets. It's not good to be close to a really low mass star, because if you're too close to it, you get this unfortunate effect that the tides of the gravity, which are very strong if you're close to a star, tend to force only one side to be pointing towards the star. The same way that the moon only points one side towards the Earth all the time. That's not good, because I don't want one side of the planet to be permanently scorched, in an endless daylight, and the other side to be basically just in a permanent night, exposed to deep space in a deep freeze. That's not really my ideal conditions. But anyway, as I mentioned, these planets around Kepler 62 do seem to be, honest to God, habitable planets around that star. And this is just the tip of the iceberg, so to speak. There must be a lot of them, at least by using my loose definitions of what I'm willing to accept as being habitable. It could have liquid water. Here we're looking at how far the planet is away from its star. So the Earth, of course, is 1 astronomical unit away from the Sun. Mars is further, Venus is closer, and so some stars are brighter or fainter than the Sun. Our star is a bit hot. Most of the other stars that Kepler looked at were cooler than the Sun, so you have to get closer. These are like a bunch of Kepler planets, and you can see that a number of them, some of them are too close. They're getting too much energy. They probably boiled any water off of the surface. But some of them, a significant minority of them are at the right distance that they could be about room temperature. They could be about the temperature of the Earth. Who knows exactly how strong their greenhouse effect is? Is it strong? Is it weak? Is it too much? We don't really know. I'm ignoring all that stuff. But there are quite a few planets out there. Considering how hard it was to find these, I'll bet you there's actually, in real life, tons more, millions of them. The problem with those really low mass stars is that you're darned if you do, darned if you don't, if it's a really low mass star. Like these stars that are like only 3,500 degrees, they're little dinky stars. If you're too far away, you just freeze.
Right.
But if you're too close, you're just trying to warm up. You're so close at that point that the tidal force of that star's gravity will probably lock you into synchronous, basically where one day is exactly equal to 1 year. So
Right.
you always are unfortunately facing just one side, always facing towards your star. So that's why people don't really like, these are very numerous, these little stars, but they're not really the best ones. I have left off moons here because we don't know anything about them, although we have seen some indirect evidence that they could be habitable, perhaps underneath global ice covers. They might have global oceans of liquid water underneath. You need an internal heat source that could last a long time. I don't really want to find a planet, that's only a few hundred miles across, like a big asteroid or something like that. It'd be geologically dead. There's no plate tectonics, there's no magnetic field, there's not enough gravity to keep an atmosphere. So I don't think we really want to be looking for, or just as a habitable world. I think it has to be probably at least something like the size of Mars. Interesting thing about this diagram here is it's showing the habitable zone in our solar system as a function of time. Here we are 1 astronomical unit away from the sun. We're definitely in the habitable zone for sure. We always have been. That's the dark green. Here's Mars, which may be in the habitable zone. Here it's a little bit far out. Here's Venus. According to this estimate, when the sun started out being less bright, less powerful, 30% less luminous than it is now, Venus was very possibly in the habitable zone. Unfortunately, the sun got brighter over the last 4.5 billion years. It's going to continue to get brighter in the future. And so Venus just got hotter and hotter. It basically kind of got, it was just sitting in the same place. It's sort of, the habitable zone moved out of it, left Venus in the heat there. So this same kind of evolution, of course, would happen around other stars too. Not to be too fussy about this, but what you really want to find, if you're looking for Earth 2, you want to find not just an object which is in the habitable zone now. You're really looking for a world, a planet preferably, that's been in the habitable zone for much of the entire history up to now of its star, throughout billions of years of evolution, because it seems like life is such a complex process that to really get anywhere exciting, it may require billions of years for things to happen. And so it's not helpful to just have a planet that was briefly in the habitable zone, and then become uninhabitable. This may very well have happened to Mars, for example. That's not good enough if you really want to find your Earth 2. Last week, I said that Jupiter is almost a failed star. Our solar system, our little ordinary nothing solar system, is almost a binary star system. And the fact is, and this again is work done partly by UCLA astronomers, lots and lots of stars of planets are in binary star system. Lots of stars are in binary star systems. That is actually one of the more realistic aspects of Lucas's imagination there. Yes, he could perhaps be living on a planet that's going around in orbit of a binary star system, except, Mr. Lucas, let me ask you this. How does Tatooine, or whatever you pronounce that planet that he's on, how does it maintain a stable orbit, without burning up or freezing everybody to death when the orbit takes it too close or too far from one of the stars when you're in a binary? Hey, Lucas, it's difficult. It's much more difficult than just having, planets go around one star and one orbit like our solar system. In fact, most of the planetary orbits in a binary star system are not really stable. They're special orbits that might be stable for a long time, Basically, if you're either just a very close orbit around one of the stars, just go around one of these stars all the time, and you're far away from another star, you might last that way for a billion years. Or you have to be in a very far out orbit, like Luke Skywalker is here, where you're basically going around both stars in a very distant orbit. Those could be stable for a long time. Maybe that's long enough for life to evolve and flourish. Although, if you look at this planet, you can't say it's really flourishing. I mean, what a dump. At least you got life. Just trying to warn you of some of the limitations. Merely finding a planet that might be the right temperature for liquid water is, and a number of you have pointed this out, is not the end of the story. That's the beginning of the story of the search for, really Earth 2. Okay, and then of course I've left out some other very exotic places like rogue planets that have left their stars and are drifting through interstellar space, but are still warm and have underground oceans that are heated by radioactive decay from their interiors. That is such a mind-boggling, fascinating speculation that I think I'm going to leave it out of this course.